I'm not going to take roll. The course is so large, I'm not going to just deal with it. Plus, I think everybody who was on the wait list is now in the class, except for maybe one person. Is there anybody who's still trying to add? So I guess everybody got in. There were some drops, and great. So welcome to my thermodynamics class. Let me just remind you that I put a whole bunch of homework problems on the board last time, so please make sure that you have written those down. And recall that they're always going to be due on Wednesday, so that whole set will be due this Wednesday. Let me also note that I've activated the Blackboard system. I will be doing a variety of example problems over the course of the quarter, and some of the examples are from previous editions of your textbook. So I've actually made a JPEG image of all the example problems. I just photographed them out of the old books. And those are also available on Blackboard, so that might be something you want to look at or make a copy of, perhaps. You don't have to do it now. I have digital copies too, and I'll present them on the board with the overhead projector when I give those examples in class. But if you don't want to write all those down, then at least you'll have access to that. Also, I've made a copy of the handout that I will pass out during exams. Basically, it's the property tables from the appendix of your book. Those are also available on the Blackboard site. And of course, the syllabus and outline are there too. So there's a variety of information. And eventually, when these videos are published, I will put links there as well to all the various videos. And hopefully, I'll have those just within a few days. Last year, when I did this in my 301 thermal class, they were always available to me within like 1 or 2 days. This quarter, we'll see. Nonetheless, the quicker the better, I suppose, for those that may want to review some lectures or just want to have some fun on a Friday night and tired of Netflix videos. Well, I guess Amazon Prime has videos and Hulu has videos, but what could be better than thermodynamics? So I'm just going to continue the review from last time. You might recall that at the end last time we were talking about ideal gases and specifically ideal gases with constant specific heats. I had presented the equations that one might use to calculate enthalpy or internal energy or entropy changes. Now I want to just continue this. So we're still talking about ideal gases, and we're still talking about constant specific heats. And we're just going to continue now by specifically talking about isentropic processes. Now, if we have an ideal gas with constant specific heats and it's an ideal gas undergoing an isentropic process, basically you'll just take the entropy change equation that's in your note from last time. After all, isentropic means constant entropy, right? And just note that the final and initial entropies are going to be the same. So we can derive the following. I'm not going to derive them. They should have been derived already for you in your first thermal class. But we'll be able to show that the temperature ratio is going to equal the pressure ratio raised to the k minus 1 over k power. K being just the ratio of specific heats, which is about the last thing I wrote on the board last time. Oh, by the way, I said initial and final with regards to 1 and 2. This would apply both to closed systems as well as single stream steady flow open systems. So 1 and 2 could represent the initial and final state for a closed system, or it could represent the inlet state and exit state for an open system, a control volume problem. So just be aware of that as we're looking at all these equations. And in fact, in this class, as we'll be dealing with flow through thermodynamic cycles for much of the course, 1 and 2 generally will represent the inlet and the exit conditions from a particular device. Okay, a turbine, a compressor, a pump, something like that. Nonetheless, we can derive this particular equation. One could also note that this is related to the volume ratio. So this can also be shown as V1 over V2 to the k minus 1 power. So this is an equation we can use for an isentropic process. One can look at the pressure and volume terms and do some hocus pocus and find that the pressure ratio is going to equal the volume ratio to the K power. Again, I'm not going to go through the mathematics, but this is what we find. Right now, this is all isentropic processes if we have constant specific heats, and of course the equations that were presented were for constant specific heats in general. Now let's go to the next step, and we're still dealing with ideal gases, but now let's look at what are called variable specific heats. Okay. So in this particular case, with variable specific heats, we can't, for instance, say that the enthalpy change is just equal to a constant value of Cp times the temperature change. We actually have to recognize that we need to take an integral between 0.1 and 2 of Cp dt. This is what variable specific heats means. Variable means that the specific heats vary with temperature. Okay, I mean specific heats are functions of temperature only for ideal gases, but they're not constants now. Okay, we assume they're variable, and in fact, this is really a more accurate method if we use a variable specific heats, and you're going to be expected to use these methods as we get into our material here. Really, the new stuff we're going to start next week. So as we do this, let me also note that there's a similar equation for internal energy change, which is going to be Cv dt. That is the interval from 1 to 2 of Cv dt. I guess more specifically, I should probably write T2 and T1, since after all, we are integrating on temperature, right? So these equations can be utilized. Now, we really have two choices when we're trying to find the internal energy or enthalpy change for an ideal gas with variable specific heats. We could go into our appendix table A2, part C, which gives you the polynomial equation as a function that is specific heats as a function of temperature, and actually go through the integration. But quite frankly, nobody really wants to do that. It's easier just to note that we do have some gas tables, and since the only gas we're going to deal with in this class is air, specifically I would note that we can find data in the air tables, which is table A17. So you can actually go into the air tables at any particular temperature and look up the values of enthalpy or internal energy based on variations in specific heat and temperature. Okay? Now, that's typically what we're going to do. Okay, we're not going to go through a long integration. Why bother? It's already been done for you, and that data is presented in an appropriate appendix. So this is something we're actually going to be talking about at length here shortly. For those of you who had a different instructor for ME301, you may have already talked about variable specific heats and understand already how to use table A17, but if you had me in 301, then we never talked about table A17. In fact, I specifically said, don't worry about it, we'll get to it in the next quarter. Just concentrate on constant specific heats to understand the basic processes. And now we're going to start looking at some more detailed information, certainly more accurate. In fact, as the book talks about analysis based upon variable specific heats, it calls it exact analysis. When it talks about analysis based on constant specific heats, it talks about approximate analysis. So we're going to be dealing, well, with both, but certainly the emphasis is going to be on the exact analysis using equations of variable specific heats and using data from table A17. Now, I should also show the entropy change equation here, because we already have to find entropy change. And again, we're not assuming constant specific heat. So basically, we just have the equation, the integral from 1 to 2 of Cp dt over T, then minus r natural log P2 over P1. And then we have the ability to modify this now. So this equation was already in your notes from last time. Certainly you covered it in ME301. But now what we want to do is go one step further. So the first thing I want to do is just open up this integral. What we could do, and hopefully you remember doing this in your integral calculus class, we could just turn this into an integral from 0 to T2 of Cp dt over T, and then minus the integral from 0 to T1 of Cp dt over T. So that's the same as this first term, and then minus r natural log P2 over P1. Now, please note that these terms here are only functions of temperature as well. So they're actually presented for you in table A17, or really any of the other gas tables, like from table A17 all the way up to about, what, 825 or 6 or something like that in your textbook for other gases. But again, we're only going to deal with air. So what we do is we define a new term here. We'll just call it S superscript 0. Different authors of different books have different names for this. Sometimes it's called a compression function, sometimes an isentropic compression function. I personally just like to call it an entropy function. But still, we're going to let the integral from 0 to any temperature of Cp dt over T just equal this entropy function. And therefore, the entropy change for any particular process is just going to be S superscript 0 at point 2, which is really T2, minus S0 at T1, and then minus R times the natural log of the pressure ratio. So this is an equation that we may need to use occasionally as we're trying to find an entropy change for a process that involves an ideal gas that is considering variable specificities. Next, what I would like to do is note that in many, many cases, we're interested in analyzing ideal, or if you will, isentropic processes. So continuing with ideal gases and variable specific heats, what if we have an isentropic process? So we already looked at that over here for constant specific heats. These are the equations that were developed. But now we need to use variable specific heat, so we're going to use the equations that are shown here above. So basically it's isentropic, so there's no entropy change. The left side of the equation is just 0. And then the entropy function at 2 minus that at 1 minus R log of the pressure ratio. And now what I'm going to do is I'm just simply going to rearrange this. And again, do just a little bit of mathematical hocus pocus, nothing special. But if we go with mathematical rearranging, we're going to end up with the following, that P2 over P1 is going to equal P to the entropy function at 2 over the gas constant R. No research data. That's never good. Glad I brought my own. Okay, so I carried this around with me for about 2 years and I've never used it. But I knew there would be a day eventually. So, I just have to remember to bring it back with me. Anyway, so E entropy function over R divided by E to the entropy function at 1 over R. Now, you should be able to see pretty easily how we get that. I'm just going to move the entropy function terms to the left. I'm going to have to raise both sides of the equation above E. The E is going to cancel out the natural log, which is why I have the pressure ratio. And then, of course, E remains with the entropy function above it. So this is the equation one would use for an isentropic process. Now, let's note that these two terms here have their own name. And we give it the term P sub R. This is called relative pressure. And the relative pressure is simply defined as P to the entropy function over R. So with this in mind, we therefore can plug everything into the equation above. And we get P over P1 is going to equal the relative pressure at 2 over the relative pressure at 1. Okay. Now, keep in mind that these relative pressure terms are, again, only functions of temperature, right? These entropy functions are only functions of temperature. In fact, as I go over here, I should really put a third line in this term because this is a definition. That's how we define this term, the entropy function. So I forgot my third line. But nonetheless, these are only functions of temperature. So we find, therefore, that PR data is going to exist in the same table, table A17 or any of the others. So PR data is in table A17. Okay? So the fact is, we never really do have to go through this integration process, right? All we have to do is know what the temperature is at either point 1 or point 2, and then just go into the book, and that allows us to find these relative pressures. So this is something, again, that I did not cover in my thermodynamics class, and shortly I'll talk about, well, how do we utilize this information. One thing we could do further is the following. So, furthermore, let's just note that from the ideal gas equation of state, PV equals RT. In other words, R equals PV over T. Okay, this, by the way, is specific volume. And note that R is a constant, right? It's going to apply at point 1 or point 2 or at any point. So this is also going to equal P1 V1 over T1 to equal P2 V2 over T2. I mean, it's a constant. It applies at any point. We can now rearrange this. So we get V2 over V1, and then you can see that the pressure and temperature terms move over to the other side. So we have T2 over T1 times P1 over P2. And then we would simply note that P1 over P2 equals, well, PR1 over PR2, right? So this is then T2 times PR1 divided by T1 times PR2. And then just continue with this rearranging. We would like to put the 0.2 terms and the 0.1 terms together. So let's just show this as T2 over PR2 divided by T1 over PR1. And then these terms, this ratio of temperature to relative pressure, it too has its own name. So that's going to be called VR, which is the relative specific volume. Okay. It's not even a specific volume term. It's just another entropy function, isn't it? Or really a temperature function based on the relative pressure, which is of course based on these entropy functions. It's only a function of temperature. So VR is going to be defined, I'll include my other line, as just T over PR. And then what we want to do is note, therefore, that V2 over V1 is going to equal, well, relative specific volume 2 over the relative specific volume 1. So this is another term that we're going to use very frequently as we solve different types of processes. So again, keep in mind, this applies only to isentropic processes, right? These equations apply. If you're doing a problem, and again, we'll look at problems eventually, but if you're doing a problem with constant specific heats instead of going an isentropic process, these equations apply. If you're going through a problem with ideal gas with variable specific heats, then whoops, this equation and this equation apply. So make sure you read the problems carefully. You might note that on the homework that I assigned on Monday, I put some little asterisks and I identified certain problems as constant specific heat and others as variable specific heats. So make sure you use the appropriate method. Again, they're only functions of temperature, so VR data is also in table A17. Okay. Now, what would a typical problem look like that's isentropic? So, just so you know what we might want to use this for. Okay. So, again, isentropic processes, ideal gases, variable specific heats, typical problem. Okay, so what would a typical problem look like? Okay, so, in a typical problem, we're going to know state 1. It's going to be the initial state for a closed system problem. It will be the inlet state for a single stream steady flow open system problem, but we're typically going to know state 1. And either the final pressure or the final specific volume, or I should say or the exit pressure or exit specific volume. So these are typically going to be known to us. Now we would note that at T1, we simply go into table A17 and we can look up PR1 or VR1. We're not going to do both. It really depends on whether we know the final pressure or the final specific volume. Right? If we know the final pressure, we're going to be interested in using the relative pressure. If we know the final specific volume, then we're going to be interested in using the relative specific volume. So we're going to go into the table at T1. We're going to find the relative pressure at that point 1. And then we're going to use P2 over P1 equals PR2 over PR1 in order to find, well, let's see, we know the first state, we know P2, we know PR1, well, we'll obviously use this to find PR2. Or, if we know the specific volume, then we're going to use V2 over V1 equals VR2 over VR1, and we use this again to find the only unknown, which would be VR2. And now that we have PR2 or VR2, relative pressure or specific volumes, then it's just a matter of going right back into table A17 at that value of PR2 or VR2 and just looking up the data we need. That we need the final temperature, we need the final internal energy, or it could be exit temperature or internal energy, or enthalpy, or entropy, or whatever it happens to be. Right? So the last step then is to use PR2 or VR2 in order to find data at state 2. Again, in table A17. Okay. Now, is this really any different as far as the procedures we use compared to when we have constant specific heats? Well, no. In constant specific heats, we're using specific equations, right? Like P2, like T2 over T1 equals P2 over P1 to the K minus 1 over K. That's how we're going to get from point 1 to point 2 if we use constant specific heats. If we use variable specific heats, it's not quite as simple, but the procedure's not much different. You know state 1, you know either P2 or V2, and now we're just going to use table A17 data with relative pressures or relative specific volumes in order to find our thermodynamic property data at state point 2. So that's the procedure. I will note that you're most certainly going to have to use interpolation to find the data. I mean, it's very unlikely going through this process that you're going to find a value of PR2 or VR2 that are specifically listed in the property tables. So you're going to have to interpolate. So make sure that you remember how to interpolate and shouldn't have any problems. Okay, so are there any questions on this material? Again, this is new, but it's not complicated. It's just a different way to approach the problem. In fact, I would guess that many of you have already read about this because this is the method that is discussed in the textbook. Even though I didn't require it in my first course in thermo, it was still there. I had plenty of students that used this method to solve problems, even in the ME301 thermodynamics class. But now we're going to have to use it for sure. So again, no questions. I will move on. So we're done now talking about ideal gases, new topic. Now we're just going to continue the review and talk about the first law. So I'm sure you know that essentially every problem we solve is a first law problem, right? We're always interested in processes. We analyze them using the first law, which can be called conservation of energy. The first law certainly has different forms. It really just depends on whether we're dealing with a closed system or an open system as to which version of the first law that we use. So if we happen to have a closed system, then the version of the first law we would use is this one. The format of this equation might be a little bit different. Often we would put the work term on the right-hand side as a positive, or we could move it to the left-hand side as a negative. That's what I'm going to do here. So Q12 minus work 12. This would represent a closed system, so 1 and 2 is initial and final state. So the heat added minus the work done by the system is simply going to equal the change in the energy, right? And that energy could be internal energy, or kinetic energy, or potential energy. So we will put all three on the right-hand side of the equation. So we have U2 minus U1, there's the internal energy. We have the kinetic energy, 1/2 mv2 squared minus v1 squared. And then we have potential energy, which you may rather call the gravitational potential energy, but this would represent the first law for a closed system. Please note that this is the change in kinetic energy. Often I'll just abbreviate the whole term as a delta KE, and this would represent the change in the potential energy. So sometimes as I go through these problems, I'll just write delta PE, but we know what these terms are. I might also note that if we just divide through by the mass, we have a mass-specific version of this equation. So just divide out the mass, and we have lowercase q12 minus lowercase w12 equals, and then we would note that the total internal energy is just the mass times the specific internal energy. So the mass is divided out, and we're just left with the change in the specific internal energy. So again, these are all per unit mass terms, right? And then we have the kinetic energy change. Of course, the mass term is gone away. And we have the potential energy. So this is what the equation could look like. As to which one we use, it really just depends upon the problem at hand, right? Some problems give you data that is total. For instance, it gives you energy units at kilojoules or BTUs. Well, then you're going to use the first version of the equation. Others are mass specific or on a per unit mass basis. So your units are going to be kilojoules per kilogram or possibly BTUs per pound mass if we have the British system of units. So these are the equations that would apply for a closed system. Now keep in mind that as we begin talking about cycles next week, we will start with closed systems. In fact, what we're going to start with first next week is the various cycles that apply to internal combustion engines, which are really just piston cylinder devices, right? It's a piston cylinder device. The mass is fixed. They're closed systems. So that's the equation, or I should say those are the equations we might use as we analyze engines or processes involving piston cylinder devices that are within engines. All right, now what if we have an open system? So an open system can also be called a control volume. Now, specifically, I'm only going to deal with the single stream steady flow processes here. We're not going to really look very much at processes that involve more than one stream. We will eventually look at some heat exchangers, but that's not going to be until near the end of the class. But usually we have a single stream process that involves a pump or a compressor or a turbine, a nozzle, a diffuser, a throttle. Those are all single stream steady flow processes, right? So for these processes, the equation is a little bit different. We have Q dot, and usually we put CV just as representation of the control volume, just to remind us we're talking about an open system. In other words, there's going to be flow into a fixed volume, which is our control volume. So the volume within the pump will be the control volume. The volume within the turbine is a control volume. Right? The volume within the compressor, that's the control volume that we're dealing with. And this represents the rate of heat input. Now, please note that they're open systems. They're processes that involve flow. So we should have everything on a rate basis. Right? The rate of heat transfer. For a closed system, it's just the total heat transfer and the total work as we go from an initial to a final point, right? Or total heat transfer work on a per unit mass basis. Here we're interested in flow, so it's going to be the rate of heat transfer and the rate of work production that have to be included in the equation. So here we have the equation that the rate of heat transfer is going to equal m dot times, and then we have these various terms. It's the same terms we have over here, well, slightly different. We have an enthalpy change, we have a kinetic energy change, and we have a potential energy change. And this would then be an appropriate form of the first law. And I don't want to forget my work term. Really, I should call it power. The rate of doing work is the power. Okay? So here we have an appropriate first law equation for an open system. We could also divide now by the mass flow rate. And the rate of heat transfer over the rate of mass flow is just going to be heat transfer per unit mass again. So we use a lowercase q. So heat transfer per unit mass. And then that's just going to equal H2 minus H1 plus V2 squared minus V1 squared over 2 plus G C2 minus Z1, and then plus the work per unit mass. So the units are going to be kilojoules per second, which by the way equals a kilowatt, or it could be in BTUs per second, which would be pretty typical for the British system. Okay. On a per unit mass basis, it's the same units we have over there, kilojoules per kilogram, or BTUs per pound mass. Okay. Now, a few things to note. These two equations for the open and closed systems, they sure look very similar, and many students are tempted to just kind of arbitrarily use whichever one they're more comfortable with. But they're different, right? For problems that involve flow, we use the enthalpy, right? For problems that are closed systems, we use the internal energy. So you can't just arbitrarily, swap out internal energy for enthalpy. It just doesn't work that way. You have to use the right equation for the right problem. If it's a closed system problem, we'll always use internal energy. There's one exception if you have a constant pressure process, but we're not going to talk about that. If you have an open system problem, then you definitely have to use the enthalpy within the equation. A few other notes. First of all, I have used a kind of a cursive letter V to represent velocity. So please don't confuse my velocity notation with that of specific volume. Specific volume, as we've seen already even today, is more like a little pointy curved letter V. It almost looks more like the Greek letter nu, doesn't it? But here I'm going to use a cursive letter V, so make sure you understand the difference in notation. In the textbook, they just use bold-faced print, so it's obvious what velocity is, but I can't do that. I don't have a bold-faced pen. So this is the way I do that. Additionally, I would note that on a per unit mass basis, if I have a work term, I use a kind of a lowercase w with a rounded bottom. It really almost looks more like the Greek letter omega. But again, on the board, I can't show any real distinction between a capital W and a lowercase w. So my capital W's always have pointy bottoms, and the lowercase w's have rounded bottoms, and that's just the notation that I'm going to use. So again, be aware of it. You guys who have me in year one, you know this already. For the rest of you, now you know. Also, we should talk about the sign conventions here. In some textbooks and some instructors, rather than putting Q and W, you have Q in and Q out, and work in and work out. So your equation would say something like P in minus P out minus work out minus work in is going to then equal the change in energy terms. I prefer not to do that. I'm just going to have one work term or one heat transfer term, and then we have to use the appropriate sign convention. So if we have a positive heat transfer, in other words, heat input, means we have a positive value of Q. And if we have heat output, or rejection, if you will, then we have a negative value of Q, or lowercase q. Depends on the problem, right? With work, the sign convention is actually the opposite. Okay? Work output, in other words, work done by the system, this is positive. Work input, or if you will, work done to the system, this is going to be a negative value. So again, positive work, and this would also apply to work per unit mass. It would also apply to the rate of doing work, that is power. So just so you're aware of that. So that's the sign convention that we're going to use in this particular class, which is consistent with everything in thermodynamics. Let me also just note lastly that power is certainly related to the work per unit mass. It's just the mass flow rate times the work per unit mass. So hopefully that's something you remember. Now, where do we use this set of first law equations, well, really everywhere for all sorts of problems. But what I would like to do is just kind of emphasize those problems or those types of processes that we're going to use in this class. And they generally deal with steady flow devices, single stream steady flow devices, the same ones that I keep mentioning, pumps, turbines, and compressors, right? If we're dealing with a cycle, within that cycle, we have pump turbines or compressors, right? Pumps provide the work input, compressors provide work input, turbines provide the work output. So these various terms, we're going to have to apply specifically to those devices. So let me just note a few things. So for the following devices, turbine and pump and compressor, we have the following versions of the first law. Now, keep in mind, this is all the first law, right? We're still talking about the first law. For these different devices that I've mentioned here, what would the equation be? Well, first let's note certain assumptions. Typically, if we have a device like this, we're spending anywhere from hundreds to millions of dollars, right? A large steam turbine in a big central station power plant can easily cost $100 million. You want to insulate that thing well. You don't want to lose heat to the environment. So generally, we would consider these to be adiabatic devices. Remember, adiabatic means no heat transfer. And that's something we could achieve by proper insulation, or at least get pretty close using proper insulation. So if we deal with an adiabatic process, there's no heat transfer, there's no heat transfer term. So that term's going to drop out of the first law equation. Also, we would generally neglect any changes in kinetic energy and potential energy. Please keep in mind that in the real world, you don't want high velocities moving through these very expensive pieces of equipment, because that's going to erode away the inside of your turbine or your turbine blades or your pump impellers. So the speeds are purposely kept low, so there's really not going to be a significant kinetic energy change, and there's not going to be any significant height change. I mean, if you have a turbine, the steam goes in and out at pretty much the same elevation. So these are not bad assumptions to neglect both kinetic and potential energy. So what are you left with? Well, for the turbine, the power that's produced by the turbine is just going to be the mass flow rate, and then multiplied by its enthalpy change, H1 minus H2. If we're dealing with the pump, then the pump work is going to be the mass flow rate, and then times H2 minus H1. I will make a note that this is the magnitude, or if you prefer, call it the absolute value. I mean, really, the equation should give you the same thing as above, right? Just m dot H2 minus H1. But keep in mind that pump work is work input to the system, and as such, it's going to have a negative value, right, based on our sign convention. So we're just going to swap the order of H1 and H2, and this is going to be the magnitude of the pump work. Further, I might note that if we're indeed dealing with an adiabatic process and the pump, besides being adiabatic, is also reversible, if it's an isentropic process, then we would note that the entropy change can be replaced by the specific volume times pressure change. So W dot for the pump is going to be m dot times specific volume at the inlet times P2 minus P1. So often we're going to deal with these ideal pumps. And then lastly, for the compressor, same thing applies as it does to the pump. The power is just going to be the mass flow rate times H2 minus H1. Again, this is just the magnitude. And we cannot apply this isentropic equation as we've done above. This only applies to a pump. And the reason is because pumps move liquids, and this equation only applies to liquids. Okay? So let's just put a little liquids right underneath the pump. But note that compressors don't move liquids. I mean, even though the devices perform exactly the same function and they actually look very similar in the real world, compressors move gases or two-phase mixtures. We just call them a compressor, but still, the above equation here only applies to liquids, in other words, only pumps. So these are the equations that we typically use when we deal with these three specific devices, pumps, turbines, and compressors. and we will be dealing with pump turbines and compressors a lot. So, moving ahead then, when we analyze a typical pump turbine or compressor, these particular single stream steady flow devices, what we often do is want to know how the device performs compared to an ideal pump turbine or compressor. Okay? And for those situations, we define what's called the isentropic efficiency. So isentropic efficiencies sometimes can be called adiabatic efficiencies. It just depends on where you're looking. But let's talk about isentropic efficiencies. Now, please keep in mind that the isentropic efficiency is not the same thing as the thermodynamic efficiency. The isentropic efficiency is nothing more than the ratio of the actual amount of work to the ideal amount of work associated with one of those three devices. So, the isentropic efficiency for a turbine is just A to the T. By the way, this is data that will always be given to you. When you buy one of these big devices, the company that's manufactured it is going to have tested it out. They will tell you exactly what the efficiency is over a wide range of operating conditions, a wide range of flow rates, a wide range of pressure changes or temperature changes. So you'll have a performance characteristic curve, which we might just call a map, because that's what we call it. But you'll have a map for the turbine, pump, and compressor. You'll know what these are. In this class, I'm never going to give you a map. I'm just going to tell you, or the author will tell you in the problem statement, that at this operating point, this is the isentropic efficiency. But in the real world, the efficiency is going to vary just depending upon the operating conditions. But nonetheless, the isentropic efficiency of the turbine is the actual work over the ideal work. Okay. So what we're going to do is just use a couple of subscripts. A represents actual, right, for actual, and S represents ideal. Now, why S? Why don't I have like I or something like that? And keep in mind that when we talk about ideal work, we're talking about an isentropic process, right? Adiabatic reversible, that's isentropic, and an ideal turbine would be one that is indeed isentropic, right? That can't be achieved, right? In the real world, there's always losses, but it does represent a theoretical limit. So as we analyze our turbine and indeed the pumps and compressors, we're going to have to determine the ideal amount of work that that turbine, pump, or compressor would have under the situation, under the, let's say, thermodynamic states associated with that process. But then we're going to have to use the isentropic efficiency to calculate the actual work. Again, hopefully you remember this from your thermal class. So that's why we use the S, right? Isentropic means constant entropy, S for entropy. So I'm going to always put the subscripts for these processes. Now again, we could divide by mass, and we get the actual over the ideal work per unit mass. We could divide by time, or if you will, take the time derivative, and we get the actual power divided by the ideal power. They all apply. Which version you use, again, just depends on the problem at hand. If we look at a pump, we have A to the P. Now, for a pump and a compressor, these are work input devices, and as such, we're going to invert our definition. This is going to be the ideal work over the actual work. The reason we do this is because we always want to make sure that our efficiency terms are less than 1, or if you will, less than 100%. Realize that in a pump, you're putting work into the system. The actual amount of work is not only the amount of work it takes to, let's say, energize the fluid that's moving through the pump, but you also have to provide a little bit of extra work to overcome the frictional losses associated with the bearings and the fluid flow through that pump. So in the real world, the actual amount of work that is required by that pump is going to be greater than the ideal amount of work that would be required by that pump, because we have to overcome friction and other losses. With the turbine, it's essentially the same, but reversed. We get work output. The energy lost by the substance moving through that turbine, that's the actual amount of work. But the reality is that work output also has to overcome the frictional losses. So the real amount of work, that is the actual work we're getting out of the turbine, is not the same as what you would think of as the, the enthalpy loss, and it is enthalpy loss, right, associated with that flow. You also have the friction. So the actual work is less than the ideal work. Some of that ideal work, that ideal work also has to have additional work to overcome the friction losses, and as such, the actual work that we get out of that turbine is going to be less than the ideal amount of work that we get out of that turbine. So, nonetheless, as we continue with the pump, we would just write this as WS over WA, or if you will, work per unit mass S over work per unit mass A, or this could also be the ideal power or the actual power. That's going to apply to the pump. And it turns out that in this general form, the same thing applies to the compressor. Okay, compressors are work input devices. We define the isentropic efficiency in the same way. So for a compressor, we use A sub C for compressor instead of A sub P, but exactly the same as above. So I'll just put a bunch of dittos just so we know that everything's exactly the same. If you prefer, just go over here and write equals A sub C. It's the same equation. All right, now again, this was all covered, obviously all this was all covered in your thermal class, so I'm not going to go into this in too much detail. But we do need a little bit more detail. Now, let's again note that for a typical steady flow device like pump, turbine, or compressor, they're well insulated, we're neglecting any heat losses, we're neglecting any kinetic or potential energy change. So what would this look like if we want to further manipulate these equations? So let's start with the turbine. Let's just show a TS diagram. And why don't we just show a couple of pressure lines, if you will. These would just represent lines of constant pressure. This would be the inlet pressure, and this would be the exit pressure. And let's just say that that's going to be state point 1. So the real turbine is definitely going to have an increase in entropy, right? The actual turbine has to have an increase in entropy. You've learned about entropy change and the increase in entropy principle. The entropy has to increase for a real device. So in the real world, as we go through the turbine, we're going to end up at a state point 2 that's to the right of state point 1. Well, and of course below it because of the lower pressure. This would be 2A. The ideal discharge point from the turbine is going to be directly below point 1. Again, ideal means isentropic, no entropy change, and the horizontal axis is entropy, so clearly this has to be a vertical line, and this will be point 2S. Okay? I like to show the point 2S at the end of a dotted or a dashed line, okay? Because quite frankly, that doesn't exist, right? We use it as an analytical tool. First, we're going to assume that the process is isentropic, and then we're going to apply the isentropic efficiency, and then we'll be able to find the actual change associated with that substance being determined. So we do have to utilize point 2S, but we can't actually achieve point 2S. We're just humans, right? We don't have the ability to create ideal processes. We just can't do it. We need to understand it, but we can't do it. Again, it represents a theoretical limit. Now, if we look at a pump, oops, I guess I better give you the equation before I talk about the pump, right? So what does this mean from the standpoint of the equation? Well, let's go back to our isentropic efficiency equation for our turbine. What is the actual work going to be? I'm just going to write this on a per unit mass basis. Well, it's going to be the enthalpy change, right? So on a per unit mass basis, the actual work is just going to be H2 actual. I'm sorry, I have that reversed. H1 minus H2 actual. So remember, the numerator is the actual work, and in the denominator is the ideal work. Here we're going from point 1 to 2S. So this will be H1 minus H2S. Okay, so this is the equation we would use for a turbine. Let's look at a compressor now. Again, showing a TS diagram. And again, let's show a couple of pressure lines. Now note that in a compressor, we're increasing the pressure. So the inlet pressure is going to be the lower pressure. The exit pressure is going to be the higher pressure. In this case, here's point 1. The actual exit from this compressor is 2A. The ideal exit is 2s directly above 0.1. The isentropic efficiency of the compressor is the ideal over the actual. So ideal, well, equations right over here, it's just going to be H2 minus H1, although the numerator will be H2s minus H1, and the denominator is going to be H2 actual minus H1. And again, I could have written this as a total quantity, total enthalpies. I could have written this as rate equations. I could have like m dot times H1 minus H2 in the numerator, and m dot times H1 minus H2s in the denominator. I'm just not going to do that. If you use those other forms, the mass or the mass flow rate terms are just going to cancel out of the numerator and denominator anyway, and you'll just end up with this equation nonetheless. So you're always going to end up with the equation on a per unit mass basis. In other words, you're always going to use specific entropy data in solving these equations. And then lastly, what if we had our pump? So again, a little diagram moving from a lower to a higher pressure from P1 to P2. Here's my point 1. Here's my actual 2. Here's my ideal point 2. The pump equation is going to be H2s minus H1 over H2 actual minus H1. However, I'm going to modify it, right? Just like I showed over here, if we have an isentropic process associated with a pump, then the enthalpy change can be converted into specific volume times pressure change. So this is going to be specific volume at 1, P2 minus P1, and then in the denominator we'll just have to leave the enthalpy terms, H2 actual minus H1. So this is the equation we would tend to use for a pump. Now, by the way, we wouldn't have to use this version if we had good compressed liquid data in our textbook, right, in our table A7 for water, for instance. But again, table A7 starts at such a high pressure, it becomes practically useless to us. So if we want to solve a problem involving a liquid, we just don't have good liquid data. What other choice do we have but to use this version? Because this is data we can just look up in the saturation tables. Okay. So anyway, let me now move on. Now, when we start looking at gas power cycles next week, they only deal with gases. So let's look at these equations and modify them based on ideal gas assumption, and let's look at constant specific heats. So let's now look at ideal gases. And specifically, we would just be looking at turbines and compressors. So what would be the turbines' isentropic efficiency? Well, we know the basic equation, right? It's just H1 minus H2A, or H1 minus H2S. I think this was derived just a moment ago, or at least presented just a moment ago. I didn't really derive it. But what we want to look at now is the case of constant specific heats. So if we have an ideal gas with constant specific heats, well, we know what the entropy is. It's just Cp times delta T. In other words, I should have said the enthalpy change is just Cp times delta T. So this is just Cp times T1 times T2 actual over Cp times T1 minus T2 ideal. And it is constant specific heat, right? So clearly the Cp's are going to cancel. And we just end up with a nice simple equation that's only a function of temperatures. The isentropic efficiency is just T1 minus T2A over T1 minus T2S. That's really all there is to it. And if we look similarly at a compressor, then, well, again, the basic equation is right over here. H2S minus H1 over H2 actual minus H1. Again, this can be just converted into a Cp delta T term, and then the Cp's are again going to cancel. So this is just going to be T2S minus T1 over T2 actual minus T1. So these are the equations we use for a turbine or for a compressor. Now, why didn't I include a pump here? Well, pumps only move liquids, and this is specifically dealing with an ideal gas, so it's simply not applicable. Okay. For gases, we only deal with turbines and compressors. no pumps. All right, so, what would be a typical problem where we would utilize this information? So, typical problem. So, typically we're going to know state 1. And we're going to typically know the exit pressure from that device. Again, this would apply to both the turbine as well as the compressor. So we know state 1 and P2. The next thing we need to do is we need to assume that it's isentropic. And when we assume the process is isentropic, this will allow us to get state point 2s. And I mean, it depends on whether we have constant or variable specific heats as to what the specifics are here. But, with constant specific heats, remember we have those equations, right? T2 over T1 equals P2 over P1 to the K minus 1 over K. Although now we have to be pretty careful because we don't just have a point 2 anymore. We have a point 2A and a point 2S. So we're typically going to use the fact that the temperature ratio equals the pressure ratio to the K minus 1 over K. But keep in mind, this specifically applies to an isentropic process. If we have an isentropic process, we don't just call it 2, we now call it 2S. So it's exactly the same equation that I dealt with at the very beginning of this lecture, but I'm just replacing the 2S, replacing the 2 with the 2S to make sure that we have the right equation. Okay? So this is going to allow us to get state 2s, in fact, specifically T2s, right? And once we have T2s, then you simply apply the isentropic efficiency equation. So A to T or A to C, depending whether we're dealing with a turbine or a pump. And we use this in order to get our one and only remaining unknown. Well, let that be the temperature, the actual temperature at the exit. So this is going to allow me to get T2A. And once we have these various temperatures, then of course, we can go back to our first law equation, we can find our enthalpy change, we can find our work, we can find whatever it is that is being required of us in our problem. Now, I will note that if we happen to have a non-ideal gas, I'm sorry, I didn't say that properly. If we happen to have an ideal gas with variable specific heats, that's a little bit different, right? This is constant specific heats. If we have variable specific heats, well, everything here applies, but the equations are a little bit different, right? We're still going to know state 1 and the pressure of the discharge, in other words, P2. We're still going to have to assume that it's isentropic to get from state point 1 to state point 2s, but now we're not going to use this anymore. What are we going to use? We're going to use relative pressures, right? As we talked about in the middle of this lecture. So you're going to use the equation, P2 over P1 equals PR2 over PR1. You know state 1, you know P2, you can find PR2, you can then find T2, and then find the enthalpies. So if it happened to be variable specific heat, so the variable specific heats, in this particular case, instead of this step, again, we're going to know state 1 and P1, we're still going to assume isentropic. In order to get state 2s, but we're not using the equation, we're now using relative pressure. P1, PR2, PR1. Again, we know P2, we know state 1, and therefore look up PR1. We use this to get PR2. And then once we have PR2, then we just continue in table 17. And and then find H2. Now, again, I have a little bit of an error here, right? This only applies for an isentropic process. I have to be very careful to make a distinction between the actual point 2 and the ideal point 2. This is isentropic, so this isn't really giving me PR2, is it? It's giving me PR2S. So let's add an S to the PR2. This gives me PR2S. We can find H2S from PR2S. Again, just by looking it up in table A17. And then lastly, we simply apply the isentropic efficiency equation in order to get H2 actual. Okay. Remember, if you have a process that is not an ideal gas with a constant, but with variable specific heats, we're going to use these basic equations for isentropic efficiency. We're going to use the actual entropies. We're not going to use Cp delta T's. In other words, we're not going to use the temperatures. Okay? So it's the same process. It's just a different way of utilizing the data. So, questions? All right. I've got just about 1 more minute, so let me just give you a very brief intro to the next topic. And by the way, Friday's a holiday, right? It's Cesar Chavez Day. You might think that it's Good Friday, and in fact it is, but that's not why we're having a holiday. This is the state of California. We get Cesar Chavez Day. So no class Friday. I'll see you on Monday. In fact, I'm not going to bother to start this 1 minute left. We will begin next time talking about heat engine and refrigeration cycles. That'll probably only take maybe 20 minutes, and then we'll start brand new material. We'll cover for the rest of the class. Anyway, any questions on anything today? All right, don't forget, you all have to show me proof of having met the prerequisites for this class, in other words, ME301. If you were in my 301 class last quarter, last year, don't bother to show me. I have your grades. I know you have. I'll just mark it out. But the rest of you, you can show me. So bring up your smart device or print it out and just make sure it's all right. So, see you all. My name is everybody.